Hello everyone, my name is Nicholas Wiley and this is going to be Material and Energy Balance Homework 5 Parts 2 and 3. We're going to do both together. I almost accidentally did them both together, so I thought why not, let's just do that. So instead of typing everything out, I do have a Word doc with all the information, but we're going to refer to that after we get through this. So before anything, what I want to do is I want to discuss what exactly we are wanting to do here. Can't find my mouse, so let's pull up our tab. So what we're going to want to do is we're going to start from our energy balance equation, which I will give. We are going to determine and derive the equation that we're going to use to solve and determine the adiabatic flame temperature. So let's start off with what equation we are going to be using. So this is a known equation. So what we have is we have the change in enthalpy here is going to be equal, I wish I didn't do this now, is going to be equal to the partial derivative of this enthalpy with respect to time. You're going to understand. I just thought I'd explain it without actually showing it at first. And this is going to be held at constant pressure. Now, in addition, what we have with this equation is we also have this, the same thing. Since we have that at constant pressure, what we're going to do is we're going to take the partial derivative of enthalpy with respect to this pressure, holding the temperature constant, and let me add the dTs. Now, the thing about this, though, is since we have an ideal gas, this has become completely irrelevant. We have no care whatsoever about the pressure because there's no energy being lost because this is an ideal gas. So what we're going to do is we are simply going to erase this to the best of our abilities. I think that is good enough. Now, hopefully you can sort of tell what that says. I know it's very difficult. But moving on. So now that we have this equation, what we want to do is somehow determine the temperature. Now, if you look, we do have this, that changed. We have this dH value, and we also have this right here. So how are we going to be able to use this? That's the real question. So what we're going to do to use this is we need to integrate. So when we integrate this right here, what we're going to get is simply just the integral from our first initial enthalpy to our second enthalpy with respect to enthalpy is going to equal, now, side note, what this expression right here is, I think I can lasso this. Now what this is known as is this is going to be known as what this is going to be known as is this is going to be known as our CP value, which is our specific heat at a constant pressure. Now, knowing this, what we can do, having this integral, knowing that, and when we do this, all we're pretty much going to get is the difference in enthalpies, difference in energy, which is very nice. So what this is going to equal is we're going to transform this into from T1 to T2, and we are going to have our CP dt. And this right here is going to be our big equation that we are going to need. This right here. So what this is going to tell us is this tells us that, again, just to reiterate, our this is going to tell us the difference in enthalpies, difference in energies, and what this is going to equal is it's going to equal our CP value from temperature 2 to temperature 1. And knowing this is going to give us the change in temperature when we reorganize and integrate properly. So moving along, I'm going to pull up what we need to do next. So I have this document right here, and I had planned on using this before, but pretty much what you can see is that we have this right here. This is our relationship after reorganizing. We got what I just showed you. So this is going to give us, I'll just make what it means. It is going to give us the enthalpy change is equal to the CP value, right? In relation to delta T, I guess we could say, the change in temperature. So what is this CP value? Going to ChemCAD, equation 107, what we get is we get this exact equation, right? And what we're going to want to do, so that was part 2, is we are going to use this equation to solve for the temperature. So now what we're going to do is we are actually going to derive the expression. So in the ChemCAD expression for CP, and integrating this from the standard state temperature to the desired temperature T. You can use Wolfram alpha as you record to show your integrations. Write a function to calculate this enthalpy. Now, I think that I'm going to include that in the next video as I have a different arrangement for when I do the actual coding. But what I'm going to do right now is I'm going to integrate for the least, at the very least. So what we have is this equation, and what I've done, I'm going to get rid of that. What I'm going to do is I'm going to plug this in. For time's sake, what I did was I spaced it out so that I didn't have to bore you with a bunch of typing, and it might take a little bit of playing with, but you get the idea. So when we do this, let's just add this to the bottom. So what we're going to get for our integral for CP, integrating CP is going to give us AT. That's an easy one. A dt is just, the integral of A dt is just equal to AT. Plus, and what we're going to do is we'll add an extra space, extra bracket, and let's grab this right here. Now this is just the what's inside of the bracket, but we are going to subtract, not subtract, we're going to set b to the side and just include it in our integral, in our expression after. So when we do this, we get that. I think that that should give us what we need. Yep, that is perfect. So when we integrate this function right here, what we're going to get is hyperbolic cotangent, which we can just trade to, and we have to multiply by b, so it's going to be BC divided by, well, let's just include all of this together. BC divided by hyperbolic tangent, since this will be easier, C divided by T. I believe that should be good. All right, so that's our first expression, what we're going to get from these parts so far. Now what we're going to do is we are going to use the second part. We're going to do the same thing. Well, I guess I can just plug in the E value, plug in E for C again, and cosine, and we plug it, and we chug it. All right. So, yeah, okay, that's right. So then what we're going to do after is we are going to, so it's E over T squared, D, E over T squared, everything looks right. Okay, all right, so continue on. AT, and then what we're going to do is we are going to subtract DE, what, some brackets, DE divided by hyperbolic tangent of E divided by T. And I believe that should be the end of our function. So what we're going to do, we just integrated this, and what we are going to be using is we're going to use this to calculate enthalpy, which in the end is going to help us solve for temperature using this this relationship up here, also the relationship that I very shakily drew right here. So that was it for this video. Thank you for watching, and I will see you in the final part of this video. Thank you.